Alright, welcome back. We're in the last video for topic 9, talking about reaction yields. This is where we left off in the last video. When the amount of product that you calculate using stoichiometry, this is known as the theoretical yield. So if we look back at the problems that we were doing previously, let me get to the slide where we have our work. So the amount that we calculated using math, right here, this 0.291 grams, for example, that's your theoretical yield. Basically what that means is, hey, I've done the calculations. If everything goes perfectly to plan in the lab when we do this chemical reaction, this is the amount that we should get, theoretically. That's why we get that term. But everyone knows that when you actually do a chemical reaction in the lab, nothing goes according to plan perfectly, right? There's human error, there's experimental error, there's all kinds of things that can get in the way. So when you actually perform the experiment and you get your measured quantity, that's usually going to be a different value, and that's known as the actual yield. So to figure out your percent yield, you would do your actual yield, what you get in the lab, divided by your theoretical yield, which is always from calculations using stoichiometry, times 100. Ideally, if the actual yield and the theoretical yield are the same, okay, right, the same number, well then that would be just the number 1 times 100, that'd be 100% yield. That's what we're aiming for, 100% yield. Anything above 100% or below 100%, that's just more off than we are from the real values. Basically, we're getting less accurate the further away from 100% we go, in both directions, right? If you get 110% yield, that doesn't mean extra credit. That means you've done something incorrect. So with that being said, looking back at example 8, this is from the previous video. This up here is the exact same scenario. It's defining that reaction that we just looked at in the previous video. So the question is saying, if you actually performed this lab and you obtained 0.278 grams of the precipitate, what would be the percent yield? So remember, percent yield is always your actual divided by your theoretical and then times by 100. So it's saying if you actually perform this lab, so you end up getting 0.278 grams. Theoretically, though, we know we should have got, what was it, 0.291 grams. That's what we figured out from calculations. So 0.291 grams is theoretically what we should have gotten. Divide those two numbers and times by 100. Remember, percentages are dictated by significant figures, and so 0.278 and 0.291 are both 3 significant figures. And so I'm going to record my percent yield with 3 sig figs. And I end up getting what? 95.5%. That would be the percent yield for this particular reaction. Not too bad. Like I said, the higher up or closer to 100% we can get, the better. So this concludes topic 9. There are some more examples here, example 9 and 10. You could actually do those on your own. Thinking about it, we could probably do example 9 right now. We'll do one more example. Example 10 you can do on your own. And if you have questions, you can let me know. But I wanted to keep these videos short. But let's do one more example just for, you know, the fun of chemistry, right? So let's read this problem here. Aluminum metal reacts with 15.32 milliliters of a 0.5 molar hydrochloric acid. Very simple. Aluminum is reacting with hydrochloric acid. So let's write that up here. Aluminum, and that's a metal, so it's going to be solid, plus hydrochloric acid. Remember, that's HCl, and it's always AQ for an acid. So this is a single replacement reaction. Remember, for single replacement reactions, you need to check the activity series. Aluminum has to be higher in the activity series than hydrogen. So we need to check that. It is, you know, I know. So, but make sure you check those, right? Because if it's not higher, this actually is a no reaction. But aluminum is more reactive, and so aluminum is going to bond to chlorine. So when aluminum bonds to chlorine, ask yourself, what's that formula going to be? Aluminum's +3, chlorine's -1. So we need to actually write AlCl3, right? If I look at my solubility rules, it's aqueous. Also, you can figure out that it's aqueous because you're in an aqueous solution over here, so it still needs to be an aqueous solution over here, right? And then plus, well, if aluminum is reacting with chlorine, hydrogen is the element that gets booted out. So hydrogen is now the element that has been replaced, but we can't write just H, it has to be H2. And that's a gas, right? It's because hydrogen is a gas. If we were to balance this, I'm just going to do it really quick. 2, 6, 2, and 3. That's our balanced chemical equation there. All right, let's write the numbers that we were given right below. So we were given the mass of aluminum, 0.0142 grams. And then for the hydrochloric acid, we used 15.32 milliliters. And the strength of it is 0.500 molar. And the question is, how many milliliters of the gas, which is the hydrogen? So how many milliliters of the gas are going to be produced? Reminder that as long as the reaction is done at STP, which it is, we can use the equation or the conversion that 1 mole of any gas will occupy a space of 22.41 liters. So with that being said, let's do our stoichiometry. Let's first start with the aluminum right here. So if I were to use up all of that aluminum, how much gas can I produce? So first step of stoichiometry, convert it to moles. All right, so we got our grams of aluminum there. Since it's grams of a solid, I can convert that to moles simply by doing my molar mass. And so there are 26.98 grams of aluminum for every 1 mole. So my grams will cancel. Ooh, there we go. Next step, step number 2, use your mole ratio. For every 2 moles of aluminum I react, 3 moles of hydrogen will get produced. So 2 moles of aluminum on the bottom, that way moles of aluminum will cancel. And 3 moles of hydrogen gas on the top. And then finally, I don't want to know moles of hydrogen gas, I want to know grams, or not grams, I'm sorry, milliliters. So I know that any gas, and remember this is only true for gases at STP, 1 mole of any gas will have a space of 22.41 liters. So 1 mole of any gas, in this case it's the hydrogen gas, will occupy a space of 22.41 liters. Now I don't want to know liters, I want to know milliliters. And so I'll do one final conversion. 1 liter is 1,000 milliliters. That way I'm in the correct unit of volume. If you want to combine these two and say 1 mole is equal to 22,410, just multiply it by 1,000 here, that's totally fine. But nevertheless, that's our setup there. I'm going to take a calculator here and calculate out what my answer would be. All right, and it looks like with 3 sig figs, because of my molarity and not my molarity, excuse me, my mass here, looks like 17.7 milliliters is the amount of hydrogen gas I could create if I used up all the aluminum. But we don't know yet if that's the actual answer. We have to also calculate now, hey, what if we used up all the hydrochloric acid? So 15.32 milliliters of HCl. Remember, how do we convert milliliters of an aqueous solution to moles? We use our molarity, right? So 0.500 molar is our concentration. So that means there's going to be 0.500 moles for every 1 liter or for every 1,000 milliliters of solution. That way the milliliters will cancel. Next comes my mole ratio. For every 6 moles of HCl, because that's what we're in up here. There we go. HCl. 3 moles of hydrogen are going to be produced. We're still solving for hydrogen, so I still want to get to that. And then I want to get out of moles of hydrogen into milliliters. So in this one, I'm just going to actually combine the steps. 1 mole of hydrogen, 1 mole of any gas, will occupy a space of 22.41 liters or 22,410 milliliters. I'm just going to combine those. That way I can save myself some space here and some time. All right. And I'm calculating those out. And it looks like I may have done an incorrect calculation on somewhere along the way. Let me just double check. Oh, I didn't divide by 1,000. I was like, something doesn't seem right. Okay. There we go. 85.8 milliliters would be the amount of hydrogen gas I could create if I used up all of the HCl, which when I compare these two, 85.8 is not going to happen. We're going to be limited by the aluminum. Aluminum is our limiting reactant. That's going to dictate how much is made, and it's 17.7 milliliters of hydrogen gas. Like I said, I'm not going to do the last example 10 because of time, but I cannot stress enough, stoichiometry is so important for chemistry. After going through topic 9, because we're at the end now, if you still are not sure about stoichiometry, even if you are sure, practice, practice, practice. You need to get to a point to where you can do stoichiometry problems like 3, 4, maybe even 5 in a row with no mistakes. It gets to a point to where you're just like, okay, this is getting repetitive now. If you can't get to that point yet, you haven't done enough. So please make sure you do yourself a favor. Make sure you give stoichiometry enough time, enough practice. It's definitely an important concept. It's not going away. Even when you get to Chem 152, it's more stoichiometry. So do yourself a favor and give it the time and attention that it needs. This completes topic 9. I will see you in topic 10.